Welcome to the Bodhi Academy. My name is Amisha Kulaso, and in today's video we will continue with our class 12 chapter 2 electrochemistry. So now in today's video we will learn how to measure the electrode potential of zinc using SAG. So previously we have learned all the concepts of SAGs and how the Daniell cell actually works. We also learned how to represent a given Daniell cell equation in the form of symbols. Okay. So now we'll learn today how to measure this electrode potential of zinc using standard hydrogen electrode. Now here in this setup, one side we have the SAG and the other side we have the zinc rod dipped in ZnSO4, and that we have considered it to be on the cathode side. Now one important thing about SAG we know is that its standard electrode reduction potential as well as its standard electrode oxidation potential both are equal to 0. Okay, so now here if we have to write the equation, that is E naught cell equals to standard electrode potential. Okay, so now I can write it as E cell equals to E cathode minus E anode. Now in this case at the cathode we have Zn, so we'll write it as E Zn2 plus to Zn, and here at the anode we have E H plus going to half H2. Now we know that any potential oxidation or reduction for SAG is 0. So we'll say that E Zn2 plus Zn minus 0, because this part becomes 0. So therefore what we see here is that E naught cell will directly be equal to E Zn2 plus upon Zn. Now this reading that we get is through the voltmeter that is connected over here. That reading comes to, when recorded, it comes to minus 0.76 volts. So now when the reading is minus, what does it indicate? So the next question that comes is, what does E naught cell value being negative, what does this indicate? So now if the E naught cell is negative, what we can say is that the hydrogen cell that is there, hydrogen SAG setup that is there, in that the H2 is said to be more stable than the other metal that is present over there. So now we can say that E naught of H2 H plus half H2 is greater than E naught of Zn2 plus slash Zn. Now why is this so? This value is what we know, it is 0, and here we have minus 0.76, correct? So obviously this part, if you look on the number line that is there, we have 0 and then we have the negative value. So here in this case 0 is greater. So we can say that any metal whose reduced state is less stable won't undergo reduction but will undergo oxidation by oxidizing itself and act as a strong oxidizing agent. Now what does it mean? So if we say if the value is negative, we can say that the H2 which is present is more stable than the reduced state of the metal. Now in this case what we'll say, if we have say now zinc, so Zn goes to Zn2 plus, it is getting oxidized, and then we have Zn2 plus which is going to Zn, that is getting reduced. So in this case now, because the value of Zn is minus 0.76, we can say that this oxidation reaction will occur more than the reduction reaction. This reduced state we won't be able to see much because this is comparatively unstable. So that is why we say that any metal whose reduced state is less stable, it won't undergo reduction, but it will undergo oxidation by oxidizing itself, and therefore it will act as a strong oxidizing agent. Now similarly, let's look at the measure of electrode potential of Cu using SHE. So our setup will remain same. One side we will have SHE, and on the cathode side we'll have the Cu rod, and we'll have a solution of CuSO4, correct? Again same way, E naught cell will be what? Equals to E cathode minus E anode. So here our cathode is E Cu2 plus and Cu minus E H plus going to half H2. So here again we know this by SHE it is 0. So we'll have E Cu2 plus and Cu. So therefore E naught cell will be equal to E Cu2 plus slash Cu. Okay. Now what we can say here is that the voltmeter reading for this is 0.34 volts. It is plus 0.34 volts. So now in terms of copper, what we can say, that copper, the reduced state of copper is more stable than that of the hydrogen, correct? So in this case if we take copper, so copper going to Cu2 plus, since its oxidation state, and then Cu2 plus going to Cu, that is its reduction state. So in this case what we will say, that this state is not favorable, correct? The reduction state is more favorable because its E cell value, E naught cell value is said to be positive, which tells that its reduced form is more stable than the H2 that is present. If the standard potential is positive, it indicates that H2 is less stable than the reduced form of the given metal. Now next, let's look at the Nernst equation. So now till now whatever reactions or electrode potentials we determined, in that all of the concentration of the product and the reactant we were considering it to be unity. When we say unity, it is going to be say 1 molar or 1 mole per liter. Now but in reality this is not always the case that happens. So Nernst equation, it says that you can remove electrode potential of any given cell at any concentration. The concentration can vary from starting from 0 to any other value. But when initially what we were considering, till now we consider it to be unity. Now from here we will see what happens if the concentration is being varied. So the formula for Nernst equation is E Mn plus going to Mn equals to E naught Mn plus M minus RT upon Nf ln M upon Mn plus. Now first let's understand what are the various terms that are involved in this equation. So to start with, first we have E. E is the reduction potential. Then we have E naught, that is the standard reduction potential. R we know is the gas constant, that is 8.314 joule per Kelvin per mole. Okay, so then we have the temperature in Kelvins. N is the number of electrons that is present. That is like if you are giving 2 electrons or if you are receiving 2 electrons. In that case, only the number of electrons, that the give and take of the number of electrons that is happening, that is considered. F we know is the Faraday's constant, that is 96487 coulombs per mole inverse. Then we have the M, which is given here, is the concentration of any solid. M we know it is considered as the solid because we take it in zero oxidation state. So anything that is there as a solid and is in zero oxidation state, we consider its concentration to be unity, that is 1. So Mn plus will be equal to the concentration of Mn plus ions that are present. Now let's considering all of that, say we can write the above equation as N plus going to M will be equal to E, put a bracket here, again M n plus m naught minus RT NF ln of, for solids we said it is 1. Okay, so we can directly substitute here 1 upon mn plus. Okay, so now the same thing if we apply this for the Daniell cell. Okay, in that case what we'll get, m will have, okay, first let's write down what happens at anode and cathode. So at anode we have oxidation. Okay, so in that case what we will write, E Cu2 plus Cu will be equal to E naught Cu2 plus Cu and minus RT NF ln of 1 upon Cu2 plus ions that are present. Same way at cathode, reduction. Okay, so one mistake here, this is also going to be reduction, because previously we have discussed by convention we only take the reduction potential of a electrode. So here also we'll have E Zn2 plus Zn will be equal to E naught Zn2 plus less Zn minus RT NF ln of 1 upon Zn2 plus. Okay, so these are the two equations that we have. Now E cell, if we have to write, we write it at E cathode minus E anode. So we have to basically substitute this part of the reaction. So E cathode is what? So E cell will be equal to, E cathode is E naught Zn2 plus slash Zn minus RT NF ln of 1 upon Zn2 plus. Then we have this minus sign, and rest will write E Cu2 plus slash E naught minus RT NF ln of 1 upon Zn2 plus. Now we will open up this bracket, so we'll get E naught Zn2 plus slash Zn minus RT NF ln 1 upon Zn2 plus, minus into this minus, then E naught Cu2 plus Cu. Now this minus into minus will become plus, so we will get RT NF ln of 1 upon Zn2 plus. Okay, so this is the equation. Now we can take out the common terms. So this and this we can take out. So E naught Zn2 plus less Zn minus E naught Cu2 plus slash Cu. Now what is common will go inside, so we have minus RT upon NF ln of 1 upon Zn2 plus and plus RT NF ln of 1 upon, this is Cu, this is Cu2 plus, sorry, so this is Cu2 plus, this is Cu2 plus, and here we'll have Cu2 plus. Okay, now here we have some common terms, so we can take them out. Okay, so we can write this as, now this part which is there over here, so we can use one identity here, that is ln A minus ln B equals to ln A upon B. So after using that, what we will get here is that this will basically be E naught cell of us. So this, if you consider, this will be E naught cell, because this is cathode minus anode. So E cell will be equal to E naught cell minus RTNF ln of, we have product will be Zn2 plus upon Cu2 plus. So this will be, this will become our Nernst equation for Daniell cell. Okay, so this is our final equation after simplifying all of the steps. So in general, what we can say for any reaction, we can say that A plus B will give us CC plus DD. That we can write as their concentration raised to their stoichiometric values. So this will be the in general formula for writing a Nernst equation. Now, how to find equilibrium constant for Nernst equation? Now, here we have studied about Nernst equation. Nernst equation has many applications. One of it is to find the equilibrium constant from the Nernst equation itself. Another one is the finding the Gibbs free energy. So first let's look at the equilibrium constant from Nernst equation. So now in Daniell cell, reaction is Zns plus Cu2 plus, that gives us Zn2 plus Cu. So now here what we can say is that as the reaction proceeds, what will happen? More and more Zn2 plus will be generated, okay, and Cu2 plus will continue to get reduced. Now as this continues, at some point the voltmeter reading will show us a 0. Now this point, when we see the 0 reading, the value on the voltmeter to be 0, it is known as the 0 reading. Okay. Now here there is no change that is happening in the concentration of Zn2 plus or in the concentration of Cu2 plus. Therefore at this point we say that the equilibrium has been attained. So what we can say now, in this case at equilibrium, E cell which is there, that is the electrode potential, will be equal to 0. So in Daniell cell, if we consider the now here we have added the equilibrium sign. So Zn plus Cu2 plus will give us Zn2 plus Cu. So Nernst equation we already know, E cell will be equal to E naught cell minus RT and F ln of Zn2 plus upon Cu2 plus. So now if we are saying E cell is 0 here in this case, what we will get is this. Okay, E naught cell with minus 2.03 RT upon NF log of Cu2 plus, Zn2 plus and Cu2 plus. So in this case what we have done, adding this 2.303, we have removed this ln and we have entered log here. Now if we consider E cell is 0, so what we can write here is that E, so this we will get it on this side. So minus E naught cell equals to minus 2.303 RT upon NF log of Zn2 plus upon Cu2 plus. Okay, so this is what we get. So now in a equilibrium setup, okay, the equilibrium constant that we write is Kc equals to Zn2 plus upon Cu2 plus. So this our whole term will become Kc. So here what I can write is minus E naught cell will be equal to minus 2.303 RT upon NF. So log of this is equal to, since we can write Zn2 plus upon Cu2 plus, that will be equal to what? Kc. So we'll write log of Kc. Also this minus sign and this minus sign will get cancelled. Okay, so we will get this equation over here. So E naught cell will be equal to 2.303 RT upon NF log of Kc. Now if we talk specifically for Daniell cell, so what we'll write here, E naught cell equals to 2.303 RT upon NF log of Kc. Now in terms of Daniell cell, the value for E naught cell that we get on the voltmeter is 1.1 volt. Okay, so now if we directly substitute that value, so we'll have 1.1 volt equals to 2.303 RT upon this NF log of Kc. Now here we have a few constant terms, so that is say 2.303 RT upon F. Okay, this all constants, if we substitute, we get a value of 0.059. So this is the constant value. So we can directly substitute it over here. So 1.1 volt equals to 0.059 upon, now n here is the give and take that is happening of electrons is 2. So we'll have 2 log of Kc. So this, if I take on the other side, 1.1 into 2 upon 0.059 will be equal to log of Kc. On solving this, we get a value of 37.288. So that will be log of Kc. On taking anti-log, we will get the log, the value of Kc over here. So this was if we are talking with respect to Daniell cell itself. So like this, for any given cell, we can find out the equilibrium constant from the Nernst equation. Now the second application that we said was about the Gibbs free energy. Now Gibbs free energy is given by, we know delta G equals to delta H minus T. Now we know some of the situations or assumptions that we consider. First one is, if delta G is greater than 0, we say that it is a non-spontaneous reaction, correct? If delta G is less than 0, we say that it is a spontaneous reaction. And this non-spontaneous and spontaneous reactions we have learned in the starting part of this first video of this chapter itself. And if delta G is equals to 0, then we say that the reaction is at equilibrium. Now, if we are discussing all of this, what is the relation between delta G and EMF? So the relation is delta Rg equals to minus NF E cell. Okay, this is a very important equation to remember. So now in this, if we consider, if our delta G is positive, we say that E cell is negative, and if our delta G is negative, we say that our E cell is positive. So in terms of standard electrode potential, simply our equation will change to delta naught equals to N minus NF E naught cell. Okay, so this will be our equation. Now if we want to write it in terms of equilibrium term constants, we can write it as follows. So we have to simply substitute delta Rg equals to what? Minus NF. And E naught cell, we know it is, we know in general, minus RT upon NF, ln of product upon the reactant that we get. So in that case, after substituting and reducing the equation, we are finally left with this equation, that is delta Rg naught equals to minus RT ln of Kc. So this was a relation between the equilibrium constant and Gibbs free energy that we derived from the Nernst equation itself. Okay, so that was it for this part of the video. In next coming video, we will solve some problems related to all of these topics to understand this better. So thank you so much for watching today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.